My name's Jamia. I'm afraid I'm going to have to stand beside the lectern because I'm a little bit vertically challenged. But I'm a senior DevOps engineer at the ABC, and for our international guests, the ABC is Australia's public broadcaster. But before I did that, I used to do, well, saying I used to do physics. Saying I'm a physicist is a bit of a stretch, but I have a PhD in physics. Typically, PhDs take 3 to 5 years. Mine took 10 years. So I'm not super good at physics. But I'm actually quite good at DevOps, and that's a reason to hire me. Not that I'm looking for a job, because my bosses are in the audience, so I'm very happy where I am, thank you. But now that I've got you locked in a room, surprise, it's time for physics. So my research, I was trying to study antimatter. The universe, most of the stuff you know that you can touch, is made of matter. From a naive point of view, we'd expect there to be an equal amount of antimatter, but there's not, which is good, because otherwise we wouldn't exist. As the universe started to cool after the Big Bang, there started to be less antimatter. But if I want to study antimatter, I would like to replicate the conditions of that early universe. So we do that by trying to create the massive particles that existed shortly after the Big Bang. So you're probably familiar with electrons and protons and neutrons. They're quite small particles. Back shortly after the Big Bang, they used to be quite big leptons. And so we want to sort of create those and examine them. The way you do that, to create big particles, you need more energy. So we accelerate the small particles that we have access to, electrons and positrons. We collide them. Because they're colliding with a large amount of energy, that energy gets converted into mass. Then we watch that big particle decay. The particle collider that I worked at was based in Japan, which is going to come up later. And so basically, particle physics sounds quite tricky, but at the end of the day, it's counting. So I wanted to count antimatter, but to count it, I needed to make it. The next thing that I sort of wanted to cover is how blind analysis at a particle accelerator or a particle research institute works. So a blind analysis is where you effectively train the model, work out what your statistical analysis is going to look like before you get access to any of the real data. So the first step is recreating the previous analysis. Typically, by this point, most analyses have been done, but you usually wait 3 to 5 years. Particle accelerator runs in the meantime. You end up with more data. More data makes a better statistical analysis. Once you prove that you can recreate the previous analysis, then you're allowed to start working on your own. So you can do things like, you've got more data, going to improve the analysis. You can use better models. Maybe time has moved on and you've got more compute and you can do more training on the models. Prove that that's working, and then you get to do what's called opening the box, and that's when you get at the real data. Then results, then graduate and publish, and then go into physics, which I didn't quite manage. Okay. So now I've done plenty of physics. Now we can get to what we're talking about, DevOps. So I said the first step was verify your analysis against the previous analysis. That's a gross simplification. When you start your PhD, the first thing, when you start your PhD, circa 2008 to 2010, I'm aging myself a little bit, you are given a desktop that is your desktop computer. You need to set up a local environment, because if you're going to develop, you need to develop against something. Cutting edge research requires cutting edge software, and that cutting edge software is written by experts in the field of physics. But the thing about experts in the field of physics is they're not experts in the area of software engineering. The package I was working with, the particle reconstruction software, was a package that they cleverly called root. So Googling that was a nightmare. Their motto was release early and release often. So keeping track of versioning was a bit of a trick. And version pinning, I don't know, perhaps that existed in 2007, but I certainly didn't see it. So I'm sure I'm sure you've all been to the previous talks, so I think you all know what the solution is there. Nowadays, we'd work in containerization. I tend to work with Docker a bit more, but I can set up a dev environment, I can give it to my devs. I don't have to spend 4 to 6 months making sure everybody's laptop is up to date. So that's sort of the first place. I would have saved a bit of time. Now I'm ready to verify against the previous analysis. And as I said, that previous analysis was performed 3 to 5 years ago. If the previous analysis is available for me to look at, that means the people that did the previous analysis are no longer available to do that analysis. They may have left the field, they may have gone to a different particle physics experiment. They're not going to be on Slack for me to chat to because it's in 2007. So if I need to repeat it, I need to work out what they did. I need to infer that from a variety of different sources. So that includes looking at their publication of their final results. That's usually a paper that's about 3 to 7 pages long, and it's not about software, it's about physics. Maybe there's conference proceedings, maybe there's talks, but ultimately I'm sort of guessing at a lot of what they did. So the only way for me to work out whether I can match what they did is I can start at the beginning, complete about a 2-week process locally, and do effectively what is an end-to-end integration test. So again, we've pretty much got a solution for that. If we'd had some version control, I wouldn't have been trying to rewrite the software locally. I work with GitLab typically at the moment. And in addition to that, some sort of unit tests. If we had step-by-step expectations of what we expected the code to do at each step, I wouldn't have had to start at the beginning to get to the end again. Okay. So now I'm about 1.5 years in. Now I'm allowed to start working on my own model. So as I said, a couple of different places to improve the analysis, generate better test data. As the field has moved on, we now have a better understanding of the physics behind it, so we can generate better test data to tag and train on. As more compute becomes available, we can create more test data to train on, so improve our statistical errors. Train the model better, again, more compute means more training time, or even use better models. So at the point I was working on it, I was trying this new thing called machine learning. Don't know if you've heard of it. I had an artificial neural network with a single layer. Very fancy. But that process is iterative and it's quite compute intense. If I want to compare different models, I effectively need to do that analysis with each of the different models, compare the statistical analysis, compare its efficiency and correctness. And research funding, I think still now, but at that time, was quite restrictive. So if you're given funding from a funding body, there are certain ways in which you can spend it. You can spend some on FTE or people or labour or postdocs. You can spend some on compute hardware. They don't mind what you spend it on, but it must be spent on infrastructure. So ultimately, that compute was provided as hardware that was bought, the previous funding cycle. So the compute was optimized for different job types at the time that made sense based on what they could afford. So there were a couple of different nodes I could run on. There was like high RAM, high compute, maybe I want to run on the short queue or the long queue that'll let me run jobs that go for more than 4 days. And that process of choosing which queue I wanted to run my integration on became almost as much of an optimization as the research itself. So sometimes maybe I want to run a short job, but I know there's a conference coming up and everybody's running short jobs, so maybe I run it on the high RAM queue, even though I'm not using that properly. So that was a fun exercise in game theory, but wasn't exactly physics. And again, nowadays, we've very much got a solution for that with the use of distributed computing and containerization and serverless. We can run what we need when we need it instead of committing to making decisions on what we think we'll need 5-7 years before we need it. Although I'm not sure if research can still use that yet, often the funding doesn't cover that sort of thing. All right. Then a little bit of a victim of my own success there. Not to get too into it, but the analysis, the physics improved, and we had a better understanding of the mode that I was analysing. To get into it, I was looking at neutral mode. All 4 final particles were neutrally charged, which makes them quite hard to detect in the detector, which meant that we had a bias against selecting for my particle. I had to do a bit of reprocessing of raw data. So what that means, the particles are accelerating, sometimes they're colliding. The hardware is constantly recording. It uses what's called a ring buffer. So as the buffer gets full, it starts overriding itself. The hardware triggers go off when they think a collision has happened. And then that all gets written to tape for reprocessing later when we have time. The step between reprocessing from tape and getting it to the point where I could analyse it had a pretty significant bias against neutral modes. So I had to reprocess 1/3 of a petabyte of data that was on tape. And I know it doesn't sound like much, but it was a lot at the time. So that was tricky. What I needed to do then was, I was doing my best. I was not a specialist in this field. I went through each experiment and tried to reprocess the data in order. And then I got a call from the engineers in the tape center, and they asked me to stop doing that because what I was doing was I hadn't parallelized efficiently. I was getting one tape robot to do all the work for 48 hours, and then I was moving on to the next tape robot, getting it to work for 48 hours, and I burned out a tape robot. In addition to that, because of the way the funding cycle worked, we owned the tapes. We didn't own the robots. We rented them from the vendor, which meant that when there was a change in vendor, we had tapes that we no longer had access to. We did not have the hardware to read those anymore. So, that cut down on how much data I had to reprocess, which saved me time. You need to understand data science didn't exist yet. So going through each experiment, there was not really a significant consideration for backward compatibility in the schemas and software. The physicists and the electricians were putting together a schema that made sense for them. And when they made changes, they put together another schema that made sense for them, which just made the whole thing a bit longer than it had to be. Nowadays, again, we've got solutions for this. We've got data warehousing. We've got ETL, which is now a thing that exists. We've got a better sort of understanding of the field of how to manage data in a way that makes sense going forward. All right. So the next step would be opening the box, but unfortunately now it's 2011 and my particle physics experiment is located in Japan. So the 2011 Tohoku earthquake happened, which resulted in the Fukushima meltdown. And it turns out when there's not enough electricity to run hospitals and schools, they're not going to let me finish my research. So rude. So my data and my compute was all on site in Tsukuba, Japan, which is about a 2-hour drive from Tokyo. And it was all turned off. PhD scholarships last for a maximum of 3.5 years, and I did not use my time wisely. So I was now at the point where I had to get a job. Luckily, at this point, there was such a thing as a data scientist. Wasn't convinced it was a real job, but they hired me, so worked out for me. And again, nowadays, this simply wouldn't be a problem. With distributed computing, data warehousing, this is all stuff that's solved. And like, this is only 15 years ago. So I'm not really sure what my point is, but boy, that took a while. Okay, cool. So now the models have been trained, the data's been skimmed, the queues have all been gamed. It's time to generate results. And ultimately, I'm sure you're all interested. I didn't find enough for any matter. We can account for about a third of what we see. We would expect more. But that's fun. So what's the point? What's the point of any of it, really? Computational physics problems require computer science solutions. I think, similar going back to Kat's talk, yeah, the computers got us to the moon. Do we need to go to the moon? No. But we got the computers, and we use those. So sometimes the real discoveries are the problems that you solve along the way. And finally, I hope that we have all learned from my mistakes. And that's it. Thank you.
Thank you so much, Timur. That was amazing. So we do have around about 5 minutes for questions. Does anyone have any questions for Timur? Oh, yeah, we got a couple. We might go to this. Yeah, yeah.
Thanks for this presentation. The challenge that I can see from my side is that to identify the correct data points that you will be able to train your model. In the sense of nowadays with the big data, you have a lot of data points that you want to collect and to identify a pattern in these data sets. However, the problem is that finding the right data sets in that way, or the data points that you want to analyze. How you can give, like in that perspective, how you eliminate the data that's not important, or how to enhance these points to train your model. So thank you.
Do you want this to me? I can. Okay. All right,
So,
here we are.
So the beauty of the particle physics, which I definitely ran into a bit of a issue when I tried to transition out of data physics into less physical, less easily modelable fields, is we do have a good understanding of the physics. The problem is we don't understand how often things happen. So everything, when particles decay, they decay with a branching fraction. That's what we're trying to measure. But we do know what that decay looks like. So it's easy in particle physics to create a tagged data set because you can simulate quite well what the signal looks like, what the background looks like, what a scattering event looks like. And I think for me, that's very much the problem when moving into less physical machine learning sort of areas is, creating that tagged data set. So I think I don't have an answer for you because it wasn't a problem for me. But I agree that the tagged data set is the worst bit.
Thank you. I guess the technology's shifted and evolved over 15 years, and I'm just wondering, how's the process shifted and evolved to make the next person coming through and doing a PhD have an easier time or less friction when they pick up the same data from 15 years ago and the source code that I don't know if that was open source, like What's that process change been like over the last 15 years for new PhD folks coming through?
So I'm not in particle physics anymore. I did check my code into SVN. I don't know what's happened to that SVN server. I do know, look, we discovered the Higgs, and now there's a lot less interest in terrestrial particle physics. We're just getting to the point where it doesn't work inside the atmosphere anymore. I do have friends in astrophysics, and they are definitely moving towards utilising this sort of technology. My particle physics friends are doing a lot of the containerization. I also know people doing that in other fields like biology and medical science as well. So I think they're adapting some of this. Again, as I said, the problem with funding models is it's quite restricted on on what you can do with the money. So if you need to hire a postdoc, you need to hire a postdoc who is a physicist first or a scientist first. And they'll pick up the DevOps while they're doing it. And so I still think there is a bit of that friction as there's more of a move towards what your IT resources look like and what your staffing looks like.
I'm happy to run around more.
I'm happy to talk about physics more.
All right, thank you so much, Tamir. A round of applause. All right.